everyone. I hope you are doing well. So in this video, we're gonna go back to one question that was asked to me by my friend. That came from my friend, and in that question, I solved an exam of functional analysis, past exam of functional analysis, and I made 3 videos for this exercise series of exercise, and I solved two using my YouTube channel, which is this one, and then the other one I solved it, but the problem is the video couldn't complete, and then my friend asked me to if possible to make another video for them to explain the solution for the third question. And also, I would like to say to express it to mention that this program is generally made for math and local language, but this time, as I said, I'm going to speak in English because people who asked this question are English speaking people. So for people of my from my local languages, don't worry, I have a lot of videos for you. So this is a special case, and then I hope you will understand. Now, in the third question, as you can see, it was it was we were to solve these three sub questions in the third question. So you have this part where we needed to define this space. I'm not gonna go back to that one because it's just a definition, and the definition is very well known. And there was this part where we needed to uh, show to 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 find for which value of p this space is a nearby space that we're gonna address. I mentioned in the video that I made before, I mentioned that this is done where when p is equal to 2. But then here, I think I'm gonna go back to that result to see it clearly why when only p equals to 2 we have that this is an Hilbert space. I'm gonna go back to that one, and then I'm going to explain the third part where you will find a dense subspace of this, and I'm gonna it's even for this third part that I'm making this video because my friend want me to explain it clearly. So for the second part, which is for which value of p our space LPE or is an LP space, a nearby space. I have already made some computation to that end to show how we get the result. So there is a theorem that says that if you have a normal space like this, if you have a normal space like this one, is a norm, then the norm of this norm space is kappa is comes from an inner product like this, if and only if this norm satisfies what the so-called parallelogram equality. Parallelogram equality is this. Means that x norm of x plus y squared plus norm of y x minus y squared must be equal to 2 norm of x squared plus 2 norm of y squared. We know already that if we are in Rn, if we were in Rn, if we were in Rn, and we were using the the norm defined by the summation of the Euclidean norm x1 square xk square, we know already that this we satisfy this parallelogram equality x squared plus norm of x minus y square equal to 2 norm of x square square plus 2 norm of y squared. This is why we know that this Rn is a Hilbert space. Even though we started by defining this inner product in Rn, then define the norm from that inner product and prove all the Cauchy-Schwarz inequality. But it is also for this reason that we could also start by defining the norm this way and then come back to to the inner product using this parallelogram inequality. So if you have a norm space that satisfies this parallelogram inequality, then this norm comes from an inner product, and that inner product is given by this. Okay, now this is like, if you don't have, you have that your norm space has scalar field complex numbers, then you need the second part. If your norm space doesn't have like is like has like scalar field real numbers, then you don't need this second part. You only need this part, and then you must divide everything by 2. So I think this is plus here, this is plus there. This is plus there because there is no reason you have this minus sign here. You have plus here. Then so this is a result that will help us to check whether our LP, this, is with this null in case P is slightly less than infinity, or with this null in case P equal to infinity, is or not a, an Hilbert space. So let us start by the case P is not infinity. So P is between 1 and strictly less than plus infinity. Consider this sequence X. Let me show. I'm sorry, this should be just X, and this is not there, and Y like this. Consider X this sequence and Y this sequence. So let us compute. Sorry, this is not present. This is not present at all. So consider the summation x plus y and the norm of the summation x plus y square in LP. So you see that the summation is going to be, so if you compute x plus y, you're going to get 1, 1, 0, and 0 everywhere. 0 everywhere. So the only thing you're going to get is that. Then when you compute the norm of x plus y, it's just 1 plus 1 all to the power 2 divided by p, 2 over p. So it's going to give 2 to the power 2 over p. So the same thing will happen if you compute x minus y. You're going to get 1 and minus 1 here, 0, 0, and everywhere 0. So when you will compute the norm, the LP norm square of x minus 1, this is not present, and this is also not present. Uh, this is not present. When you compute the LP space of norm of x minus 1 to the square, you're going to get 1 plus 1, because the LP, as you know it, the norm is with absolute value. So if we compute the absolute value of minus 1, it's going to be 1. So you get 1 plus 1, which is again 2 to the power 2 over p. So then when we do the summation, what are we going to get? We're going to get 2 times 2 to the power 2 over p. So when we add plus 1 here, and then we make some computation here, we're going to get that the summation of the norm is going to be equal to 2 to the power 2 plus p over p. Now, let us compute LP norm of x. X is just one component here. The LP norm of x is 1. And y the same, only one component. The LP norm is 1. So the summation here is going to give us 4, which is 2 to the power 2. So this summation is going to equal this if and only if we have this equality. And this equality is going to be true if and only if p plus 2 divided by p is equal to 2. And then that implies that 2 plus p, p plus 2 must be equal to 2p, and then p must be equal to 2. So you see, for this particular case, only this particular case, x, this particular choice of x and y, choices of x and y, we have the equality, the parallelogram identity only when p equals to 2. So for the rest of the case, taking this particular choice, you see that you don't have the parallelogram inequality. If p is not 2 and p is finite, if you take any other P like that, and you take only these two choice of x, two choices of x and y, you see that you don't have the parallelogram equality. But then the theorem says that this must the parallelogram equality must hold for all x and y. So if we already found one x and one y where the parallelogram inequality is not satisfied, we can already conclude that we have a problem with these property. So we have found already that for any other choices of P different from 2, we can always find X as we chose X, Y as we chose Y, such that this is not true. This means that only when P equal to 2, we can expect to have the parallelogram inequality, not for other. So those that those other choice, when P is less than when P is finding P different from 2, they are all not coming from those norms are not coming from any inner product. Only we can only expect it to be true if P equal to 2. But then let us see, so we can conclude here that so if P is not true, LP of N is not an Hilbert space. Is not an Hilbert space. An Hilbert space. So now, what I'm gonna do is, what if P equal to 2? What if P equal to 2? So if P equal to 2, if we compute this square for any particular choice of x and y, we're gonna get this. The summation 1 to plus infinity xn plus yn square, which is equal to the summation x plus infinity xn square plus 2xn yn plus yn square. Then, if we get x minus 1 to the power my y to the power, you're gonna get 1 to plus infinity. We do the same computation. We're gonna get x squared minus 2xn yn plus yn squared. Yn squared. So then you can already see that if we add these two, and what we're gonna get, that xn x plus y square, so this is not present, plus x minus y square is going to be, this part will disappear, and then you're going to get just 2 summation of xn square plus 2 summation of yn yn square. But as you can see it, this first part is 2 norm of x square, so this is not this, plus 2 norm of y square. So this is the parallelogram equality. So you see that for p equal to 2, you have the parallelogram equality for n. So the same thing can happen when p equal to plus infinity. You can all, if you don't even need to check, it's not gonna work at all, because you only need to take the same thing. You see that if you pick um, p equal to if you take x equal the same choice 1 0 and everywhere 0, and y equal to 0 1 and everywhere 0, then you take x plus y in the infinity norm is gonna give 1, and you take y x minus y like this in the, so this is not present in the infinity norm, is going to be equal to 1, and then when you will add them, if you add them, you get 2. But if you take xn like the infinite norm, so this is not present, is going to be 1, and then the y in the infinite norm is going to be 1. Then if you add them, you multiply by 2, you're you're gonna get here 2. You multiply by 2 here, you're gonna get 2. So you add them, you're gonna get 4. When you add them, you're gonna get the answer is gonna be 4, which is different from 2. So this is what shows that for uh, only for p equal to 2, you have something, you have that your NP space is an Hilbert space. It is